Alright, this is Honors Algebra 2 Pre-Calculus, and we are back with 9.2 in Pre-Calc, which is arithmetic sequences and partial sums. So, let's talk about the sum of a finite arithmetic sequence. So remember, finite means does not have an infinite number of terms. It could have a lot of terms, millions and millions of terms, but it stops, right? And we know arithmetic means there's a common difference between those terms. So it's on page 628 of your book. The formula they give you is if you want to add the n terms, so could be 100, could be 1,000, could be 5, right, of an arithmetic sequence. The formula to do that, which we're going to call S sub n for the sum of those n terms, so sum of n terms, is going to be n over 2 times the quantity a sub 1 plus a sub n. Okay, so let's talk about what this means and why it works for a sec. So to do that, we're going to talk about a guy named Carl Friedrich Gauss. So he's a pretty famous mathematician. Some of you, well, hopefully if you've made it here, you remember chapter 4 of Algebra 2, which was matrices, and you may recall Gaussian Elimination. So you can thank Carl Friedrich Gauss for that. So Friedrich Gauss is a famous mathematician. So as the story goes, and again, I'm kind of coloring this with some of my own version of history here. Friedrich Gauss was probably one of those kids, like many of you are in class, that just gets bored when things are too easy. And he was probably bouncing off the walls and crazy, and his teacher got really frustrated, probably, I don't know, this is my take of history, and said, Friedrich, go in the corner and add all the numbers from 1 to 100. And Friedrich, in like 2 seconds, turned around and said 5,050, like super mad fast, right? And so the teacher was probably flabbergasted and infuriated and all sorts of things because, you know, she was probably pretty much over Gauss and his crazy high-energy nerdiness already. So let's talk about how Friedrich Gauss added the numbers from 1 to 100, right, the integer numbers from 1 to 100 so quickly, right? So let's look at the numbers from 1 to 100. So 1 plus 2 plus 3 plus 4 plus dot, 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 dot. Somewhere in the middle, there's a 50 and a 51 plus dot, 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 dot. Way down the line, we have a 97 and a 98 and a 99 and a 100. Okay, so all of these numbers from 1 to 100, right? So now let's look at what's happening here. So if we look at the numbers in pairs, so let's look at what 1 plus 100 is. Doesn't that add to a 101 as a pair, right? And then 2 and 99 as a pair also add to a 101, right? And 3 and 98, well, if you add that pair, they also add to a 101, right? Sorry, missed my 98 a little bit. Okay, and then 4 and 97, right? Same thing, all the way until you get to the middle where you're going to get another 101. So essentially what Gauss noticed was that each pair of numbers sums to 101, and because you have 50 pairs, because there are 100 numbers total, so half of that number of numbers would be the number of pairs. So what he did was he said, oh, it's the number of pairs times the sum of each pair, right? Like each pair, sum of each pair, right? So that's 50 pairs times the 101. Oh, hey, teacher that's totally annoyed with Gauss, it's 5050, and that's how he did it, right? So now let's look at that formula and see how that works with this other arithmetic formula we have. Notice that that's basically what this is saying too. The number of pairs would be the numbers n divided by 2, and a sub 1 is the first term, and a sub n is the last term, right? So just like we saw, I was able to figure out the sum of the pairs by using the first and last term, and then every other pair summed to the same value because that's the way this arithmetic sequence would work. And we could walk through the logic of why the arithmetic sequence works that way, but essentially the short answer is that the common differences that you have, so like this guy would have, this doesn't have any of the plus d's, right? Like this is a sub 1. This was a sub 1 plus 99 of the d's. So basically, I end up getting 2 of a sub 1 plus 99 of the differences, right? Well, this guy was a sub 1 plus 1 of the differences, and this guy's a sub 1 plus only 98 of the differences. So again, if I sum them, I'd get 2 of the a sub 1s and then 99 of the differences, and so on, right? So again, interesting that you can figure out the sum of a sequence this way. And that's what Gauss did that made his teacher like totally pulling her hair out, or his hair out, I don't know, frustrated with Gauss's existence, right? So essentially he was given like a mathematical timeout, and it totally did not pan out for the teacher. Anyway, so let's do some examples of sums of finite sequences now. So again, remember, the short version, if you're not just trying to memorize a bunch of subscripts and random letters, is that when you're adding an arithmetic sequence, you find the sum of each pair by using the first and last term as your trial case, and then you times by the number of pairs. So I believe we were on our example 4 in this section. All right, so for example 4, I'm going to give you a sequence. Let's do 5, we can go lazy, 5, 10, 15, 20, 25, 30, 35. Okay, so if I want you to find the sum, right? So I could ask you to find S sub 1, 2, 3, 4, 5, 6, 7, right? So if I want to find S sub 7, because there are 7 terms, right? I would take the number of pairs, which is 7 over 2, right? That's the number of pairs, times the sum of each pair, which in this case would be 40, right? So 5 plus the 35. So I'm going to get that this is 7 halves times a 40, right? And you might be panicking about the decimal, but if I were you, I would divide the 40 by 2 and make this a 7 times the 20, and I get that it's 140. Now, could you totally have just sat here and added to get 140? Absolutely, you could have, and it would have been fine. But what if I give you way more terms, right? So like in this example, I only gave you 7 terms, and you can see all of them, and you could totally just be like, typey, typey, type, 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 and find the sum. But that's not a realistic thing to do if I give you a lot more terms, right? So again, it's the number of pairs, right, which is half the number of terms, times the sum of the first and last term. So if we wanted to find the sum from, say, 1 to 100, as Gauss did, we could do exactly what Gauss did, and we'd find that it's a 101 times 50. Cool. So now let's talk about what if we're talking about infinite sequences instead of finite sequences. So if a sequence is infinite, so if a sequence is infinite, we can still do that's not how you spell infinite. We can still do the same sum, right? We call S sub n the nth partial sum. The reason it's the nth partial sum is it's not the whole sum, right? It's the same formula, but it says you're only summing the first n terms, right? Because if we were summing infinite terms, right? If we're summing infinite terms, that's not just the first n terms. That's all the terms ever. And so we call this the nth partial sum, okay? So in the next video, we're going to do some examples where we find the nth partial sum of an infinite arithmetic sequence.